Simpson's rule says if I've got an integral of a function f from a to b, I'm going to approximate this with this formula. It's b minus a divided by 6 times parentheses f of a plus 4 times f of m plus f of b. So a is the starting point of the integral interval, b is the end point or the upper bound of the integral, m is the midpoint. So this is a method for numerical integration where you've got to evaluate your function 3 times at the beginning, middle, and end. And the good thing, just like the Riemann sum or the trapezoid rule or whatever, is that I don't actually have to take any antiderivatives. But again, it's only an approximation. It's not necessarily the real thing. So a bit of history. Kepler discovered this method in 1615, but it's named Simpson's rule after Thomas Simpson, who later knew about this and included it in a math textbook, and then Simpson's math textbook became popular, and so most people learned about this from Simpson's textbook. A lot of math stuff is fuzzy like this, like Newton's method. Not first published by Newton, first published by others, but not in like the exact neat formula. And then later, after the fact, people discovered papers of Newton's that they believed were written before the first publication of this rule that somebody else did later. And again, not necessarily in the form of like an iterative formula or anything like that, just kind of like in the geometric sense of the idea. And then, things sort of slowly develop over time, especially around the 1600s, 1500s, 1700s. So it's not terribly important who found this or who discovered it. The story goes that Kepler actually found the formula after watching workers at a winery use this formula to estimate the volume of wine barrels. And it's likely that those workers were not mathematicians and didn't derive this analytically. They were just, we found something that worked. We found a rule of thumb that was really accurate at estimating the volume of wine barrels, and so they were just using it because they somehow figured out that it worked. And also you might notice that the 1600s is prior to calculus. At least 1615 was prior to calculus. And so even if Kepler stated this rule, it was more likely in terms of like a geometric sort of argument and not in terms of like, this is an approximation to an integral. But, oh well. Ask Dr. Brown about that in History of Math. Ask him who came up with Simpson's rule. So let's approximate the value of the following integral using Simpson's rule on the interval from -1 to 1. So a is -1, b is 1. What's my midpoint? 0. So what is f of -1? You need a calculator. I don't have a calculator. What's sine of -1 in radians? Sine of -1 in radians is 0.8415. Then, of course, I'm dividing by -1. And then sine of 0 is...
So should f of -1 be negative, since you're dividing by -1?
Maybe I misspoke. Sine of -1 is -0.8415. So negative divided by negative is positive. Sine of 0 is 0. So 0 divided by 0 is undefined. But if I were to take the limit as x approaches 0, of sine of x over x. What's that limit? 1. So that's going to be the value of my function there. And then that is also going to be 0.8415. So Simpson's rule says I can approximate this integral by taking b minus a divided by 6 and then f of a plus 4f of m plus f of b. So it's kind of like a weighted average. B minus a is 2. And then that's going to be 0.8415 plus 4 times 1 plus 0.8415. So we take 0.8415 times 2 plus 4 and then divide by 3. 1.894. Okay, everybody gets it? That's how we do a Simpson's rule approximation.
How come it's 4 times the midpoint?
It's a good question. I'm going to tell you. We're going to spend the entire day today talking about Simpson's rule. So at some point in the next hour, you'll understand why the midpoint is 4 times the midpoint. So let's figure out what the real value is for the integral of this function using handy dandy wolframalpha.com. Integral of sine of x divided by x from -1 to 1. The real answer is 1.892. So my error, my actual error, is going to be the approximation minus the true value. So that's 0.002. And if I want the relative error, I just take the absolute error divided by the true value. And the absolute error divided by the true value would be 0.002 by 1.892. It's 0.01057. Which is 0.1057%. Relative error. Super tiny. It's a very good approximation, it turns out. I said do this on Microsoft Excel, but we really don't need to. I don't know why. Maybe we'll use Excel later if the calculation gets a little bit longer, but everybody's fine with that, right? You could do that on a test. Cool. So one of the last things we talked about last time when we were talking about the left Riemann sum, the right Riemann sum, the midpoint Riemann sum, the trapezoid rule, we kind of ended our lecture here. We said, well, if an integral approximation is exact for every polynomial up to degree k, then the absolute error of its composite method is asymptotically proportional to 1 divided by n to the power k plus 1. And so if we wanted a better integral approximation, we could do two things. One, we could use more subintervals. If I got a Riemann sum, I'm going to use more rectangles. If I got a trapezoid rule, I'm going to use more trapezoids. Or my other option is I could try to use an approximation method that's exact for a larger degree. I want a larger degree of exactness because that could also shrink my error. And so as we were kind of summarizing the degree of exactness of all of our numerical integration methods so far, We said, well, Riemann sums aren't super great. At least the midpoint rule has a degree of exactness 1. There's not a convincing reason to use the trapezoid rule because it doesn't improve on our degree of exactness. And then our question for today is like, what do we do if I want a larger degree of exactness? What could I possibly do to bump that up to get a degree of exactness 2? How do I come up with a numerical integration method that would be exact for polynomials of degree 2? I'm going to show you something on Desmos that's called an interpolated degree 2 polynomial. And what I mean by that is, if I say I want a degree 2 polynomial that interpolates these 3 points, what I'm saying is find me a polynomial that looks like ax squared plus bx plus c, and make those a, b, and c coefficients just finely tuned so that my parabola passes through all 3 points exactly. And you notice that like any 3 points I choose in the plane, as long as they're not vertically one directly on top of another, that'll break it. But as long as they're not completely on top of each other, then any 3 points on the plane does have an interpolating quadratic polynomial. You can prove this in linear algebra class pretty quickly if you take linear algebra. So what we're going to do is we're going to take an integral, from the lower bound of my integral a to the upper bound of my integral b, and we're going to choose 3 equally spaced points at a, the midpoint, and b. And then we're going to use those 3 points to create an interpolated degree 2 polynomial, like you just saw, and then we're going to integrate that interpolated degree 2 polynomial. And what I'm going to show you at the end of the next proof is that integrating the interpolated polynomial is going to give us that rule. And that's why what we have at the end is going to be exact for a degree 2 polynomial. I don't know what this link goes to, honestly. I put this link in my lecture a long time ago. Okay, so this is what Simpson's rule would kind of look like. If you want to visualize this the way we visualize like Riemann sums. In blue, that blue function is the sine function. And so this is what it looks like to integrate the sine function using Simpson's rule. I've got a lower bound a that I can click and drag around. And I've got an upper bound b. And the midpoint is also marked right there. But what Simpson's rule is calculating is that shaded green area. It's interpolating a quadratic polynomial on top of the sine function, using the values of the sine functions at the endpoints and the midpoint. And then what it's doing is it's just integrating the quadratic polynomial. And so you hope in the end that the shaded green area is close to the area under the blue curve. So you get a good integral approximation. And sometimes that looks like it's a really good approximation. And other times it might not be a very good approximation, but that's the idea. So exercise 3 says derive the Simpson's rule formula starting from the integral of a quadratic polynomial interpolated at the points x equals negative h, x equals 0, and x equals h. Oh. That's pretty cool. So here's what a generic plain old degree 2 polynomial looks like with coefficients c2, c1, c0. I'm not using a, b, and c for my coefficients because I'm going to use the a and the b for the start and end points of the integral. But this is just plain old generic quadratic polynomial. He's still there. And then this is what it looks like if I plug in x equals negative h, x equals 0, x equals h into that degree 2 polynomial. You can see what happens if I add the first and third equations together. So the left side is going to be p2 of negative h plus p2 of h. And then the right side, that term is going to cancel with that term. So I lose the C1H's. What happens here? What are we doing right there?
Adding a new thing. Bringing it in.
On the right side, I'm subtracting I'm subtracting 2C0. On the left side, I'm subtracting 2 times C0, right? Because C0 is P2 of 0, so I can just replace that. Okay. Now, let's say I want to integrate this quadratic from negative h to positive h. What you always find, in this case, if my lower bound of my integral and my upper bound of my integral have the same value but opposite plus or minus sign, then any odd powers of x are going to disappear. Because when you antiderivative, they're going to become even powers of x, and then you subtract them, and so they cancel each other out. So notice that once again the C1 constant disappears. And there's a little bit of basic simplifying until this step that might look a little bit confusing, except we're going to use this definition for 2C2H2 right here. And then likewise, C0 was the same thing as P2 of 0. Do you see that happened? And this almost looks like what we want, right? Like this point right here, we're thinking that just about looks like Simpson's rule, with maybe a little bit of tweaking, because this should be b minus a over 6, and I don't necessarily want the negative h, the 0, and the h. I'd rather have a, m, and b. But imagine you take the same function, the same bounds of integration, and you just translate them horizontally in the xy plane, right? You move the function 5 units to the right, but you also move the bounds of integration 5 units to the right. You get the same integral. If I want to move my bounds 10 units to the left, as long as I also move the function 10 units to the left, we'll get the same integral. So the x coordinates are kind of chosen arbitrarily. I don't have to have this thing centered at 0 for it to work. It just happens that centering this at 0 makes the proof really quick and easy. But if you're okay with translating this left and right by the midpoint m, then 0 becomes m. And recognizing that h is just half the distance between my upper bound and my lower bound, well then negative h becomes a and positive h becomes b, and h divided by 3 would then be b minus a over 6. That is exactly our Simpson's rule. And that should, I hope, answer Ben's question. When Ben was like, why are we doing 4 times the midpoint? Well, there is a reason. Not super easy to explain unless you've got, a paper explanation in front of you to work on. But if you take a quadratic polynomial and you say, all right, I want a rule that will integrate this thing exactly given the values of my function at the start and the end and the middle, then those are the coefficients that make it happen. And if I ask you to derive this, which I could ask you to derive this like on a test, that's what I would want. Something similar to this, where I can just see the steps and I can see your logic and I understand that you know what's happening. It's okay. I would probably still give you full credit if you skipped some steps, you know? Like, as long as I know that you know why this stuff works, then you can skip some steps. You don't have to write down things like hold that thought, right? You can just put it in your own words. And as long as your own words and your own symbols make sense to me, then you can get full credit for that type of question. All right, so the absolute error in Simpson's rule is asymptotically proportional to b minus a to the 5th power. This proof is going to look a lot like the proofs that we did for the same exact kind of claims that we made for the Riemann sums, the trapezoid rule. And this type of proof goes like this. We're going to pretend, well, we're not going to pretend, but we're going to treat f, my function, by rewriting it as the Taylor series of f centered at the midpoint. That's almost always the trick in this class, by the way. If you're like, how do I start this proof? Go ahead and just write the Taylor series of f centered at the midpoint. That's almost always 90% of the time the right way to start. So here, what I just wrote down, this is the Taylor series of f centered at the midpoint. Here it is. Then we're going to say my actual error is Simpson's rule minus the true value of this integral. So capital S is going to represent Simpson's rule. We are going to once again use a little lowercase h to mean half of the distance from the lower bound to the upper bound. And so if I want the Taylor series of my function f evaluated at the lower bound a, I can use the little lowercase h in that Taylor series because h is half the distance from the lower bound to the upper bound. And that means h is the same thing as the midpoint minus a. And notice, because I have a little minus sign here instead of a plus sign, that's because what I would really normally see is a minus m here. As a Taylor series, you take your variable minus the midpoint, or the variable minus the place where your Taylor series is centered. But since h is the midpoint minus a, that's why I put in a minus sign instead of a plus sign. I also put in a plus sign for the even powers of h, because for an even power of h, two negatives make a positive, right? So even powers, the plus or minus signs go away and you just have a plus sign. Now for f of b, I can once again use the h, because h is going to be the endpoint minus the midpoint. And that's the correct order of subtraction, and so I can use all plus signs when I write out the Taylor series for f centered at m, evaluated at b. So whenever I write Simpson's rule again, take a look at this and then take a look at this. The only thing I'm doing is I'm plugging in the Taylor series for f of a and adding to that the Taylor series for f of b. So what would it look like if I add f of a plus f of b? Well, I'd have 2f of m, right, for that first term. And then also add in this for f of m, and I would get 6f of m. What about the terms that have h to the 1 power? Well, this term has negative f of m h to the 1 power. This term has positive f prime of m h to the 1 power, and so those are going to cancel each other out. The same thing is going to happen when I add these terms, because they're the same, but they are opposite sign. And the same thing is going to happen anytime I'm adding the odd powers of h, because they're going to have opposite sign. And then for the even powers of h, I just double the coefficient, because they're the same but with the same positive sign. So that gives me Simpson's rule expanded in the Taylor series of f centered at n. The next thing I need is the integral, the true integral of f. And again, I'm going to use the Taylor series of f centered at m, and I'm going to take that antiderivative, plug in b, plug in a, subtract the b stuff minus the a stuff like you would normally do using the whole fundamental theorem of calculus. And what you find again is that the powers of h that are odd powers in the integrand are going to become even powers of h after you take the antiderivative. And even powers of h are going to cancel themselves out whenever you plug in b and you let me think about this for a second. Let's write this out, because maybe I should have typed out an extra little step in here. I don't want this to be super clear what's happening. This is the integral from a to b of this function, which is f of m plus f prime of m times x minus m plus f 1/2 f double prime of m times x minus m squared plus and so on, right? Because that's the Taylor series. It goes on forever. When I take the antiderivative, evaluate at a, evaluate at b, this is going to be f of m times x plus f prime of m times 1/2 x minus m squared. Because we're taking antiderivatives. And then plus 1/6 f double prime of m x minus m cube, and so on. So now whenever I plug in the b here, and I get b minus m squared, b minus m is like h, so that's h squared. And then I'm going to plug in the a, and I get a minus m, which is like a negative h, but a negative h squared is still positive h squared, and then I'm going to subtract those. So all of these terms are going to end up getting canceled out, and you're only left with the odd powers of h. Well, so compare then the Simpson's rule and the true value. And remember that the actual error is going to be the Simpson's rule minus the true value of this integral. So whenever I go to subtract these, 2fmh is going to cancel with that one. This 1/3 f double prime of mh cube is going to cancel with this 1/3 f double prime of mh cube. And then this doesn't cancel. Look at the first terms that don't cancel. I've got 1/36 times the fourth derivative of f of m times h to the 5th power, and I've got 1/60 times the same thing. And so now you can see where 1/36 minus 1/60 happens. Now you call your 5th grade friends and you ask them to subtract fractions for you. And they tell you that 1/36 minus 1 over 60 is 1 over 90. And then what happens in this last step? How did I go from 1 over 90 to 1 over 2,880? I think there's a little mistake here. There's a typo I need to fix. This is supposed to be h to the 5th power. Okay, now you can tell me what happened in this last step. B minus a is the total width of my interval. H is only half of that. So if I want to blow this up from h to the 5th power to b minus a to the 5th power, that's like multiplying by 32. This is 32 times larger than that. So I need to also divide by 32 to keep everything balanced. And 90 times 32 is 2,880. So the error in my Simpson's rule approximation is asymptotically proportional to the fourth derivative of your function at the midpoint divided by 2,880 times the width of your interval to the 5th power. Or you could just say it's asymptotically proportional to b minus a to the 5th, which is pretty good. I mean, that converges very quickly if b minus a gets small. So it's a good approximation method. That's why we saw just a moment ago with our example that we got a really close approximation. This is what I would call a happy coincidence. Even though we just came up with Simpson's rule as a way to exactly integrate a degree 2 polynomial, it turns out that Simpson's rule actually will give you the exact integral solution for any degree 3 polynomial for free. That's pretty crazy. So we derived this so that we could get a degree of exactness 2, and it just so happens that we get a degree of exactness 3. The proof is pretty straightforward. The proof is more of just an exercise in vocabulary. Like in the last proof, we ended up with this as being our first non-zero error term. And notice that if I have a degree 3 polynomial, the fourth derivative of a degree 3 polynomial is 0. And the 5th derivative, and the 6th derivative, and the 7th derivative, they're all just equivalent to 0. And so, since I got this error expression from a Taylor series, I know all of the other terms in this expression for error, we're only going to have higher order derivatives of f. All of those higher order derivatives of f are 0. And so we have 0 error if I have a polynomial that's degree 3 or less. So we can talk about composite rules. Composite rules are like, using more than one rectangle in a Riemann sum, or using more than one trapezoid in a trapezoid rule. Or for Simpson's rule, I can break down my overall interval into smaller subintervals and do a Simpson's rule approximation on each little subinterval. That would be the composite Simpson's rule. And so if I only had one interval, the width would be b minus a, but if I have n intervals, then the width is b minus a divided by n. And that means that my error for each little subinterval is going to be asymptotically proportional to b minus a divided by n to the 5th power. But then if I have n subintervals, we multiply that times n, and we find out that the error in a composite Simpson's rule is asymptotically proportional to 1 divided by n to the 4th power. So if I were to double the number of composite Simpson's rule subintervals, in other words, if I make an approximation with 2 subintervals, and then for my next approximation, I double that, and I make an approximation with 4 subintervals, how does that affect my error? We expect the error to decrease by what factor? Yeah. The new error is going to be the old error times 1 over 16. Ish, right? Because, this is what happens asymptotically. There's other terms in the error expansion that we're ignoring, but, it's close to that. It's close to that. So the right answer is we expect the error to decrease by a factor of 16, or you could write the factor of 1 over 16, as long as you know that the error is decreasing. If we have calculated an approximation using 3 Simpson's rule subintervals, and we get an absolute error of 10, and now we want to calculate a new approximation using 5 subintervals, then what's the new absolute error that I expect? Okay, so you might not know how to work this. I'll show you how to work this problem. We say that my error is proportional to 1 over n to the 4th power. In other words, there's some constant that makes the error proportional to 1 over n to the 4th power. So if now my error is 10, I can just solve for k. When n is equal to 3 and epsilon is equal to 10. So in other words, k would be 10 times 3 to the 4th power. Okay, now, this new error that I'm trying to find is going to be k times 1 over 5 to the 4th power.
$1.296.
1.296. Very good.
Assuming that figure
Okay. Yeah, so now this is maybe a situation where I want to actually use Microsoft Excel to make this lecture a little bit faster. Obviously on a test you're not going to have Excel, but I'm trying to make this an efficient lecture, so let's do it. I'm going to evaluate this function using Simpson's rule on the interval from -1 to 1. First, I'm going to do that with 1 subinterval, then with 2 subintervals, and then with 4 subintervals. And I should say that this is going to be using composite Simpson's rule, right? Composite means more than 1 subinterval, but that's the idea. Okay, let's see if I can remember that. So n is equal to 1. We're going to have a column for A, a column for B, a column for M, a column for f of A, f of B, f of M, and we'll have a column for my approximation. Call it S for Simpsons. And so if I only have 1 subinterval, 1 interval, then this is what it looks like. Sine of the lower bound divided by the lower bound, sine of the upper bound divided by the upper bound. And then I'm going to say sine of 0 divided by 0, and it's not going to like that. So I'm going to have to just replace that with a 1, and then Simpson's rule. So Simpson's rule is going to be b minus a divided by 6 times, open parentheses, f of a plus 4 times f of m plus f of b. And that's my Simpson's rule approximation for n equals 1. Now let's try n is equal to 2. And to do this, my upper bound for my first interval is going to go only from -1 to 0, and then my next one is going to go from 0 to 1. I'm going to plug in ones where I'm trying to take sine of whatever. Sine of the thing. Hold on. The midpoint has to be the right midpoint. And we want sine of the midpoint divided by the midpoint. And now to get my total Simpson's rule, after I've done 2 subintervals, I got to add those subintervals together. Call that sum of those 2 things. And now my approximation is 1.892, which is even closer to the real thing. And then lastly, if I want to do the same thing for n is equal to 4, I'm going to go from -1 to -½ to 0, and then 0 to ½ and then ½ to 1. Okay, there's my new approximation. And I would like to do this. I would like to get the true value, which is, I don't even know how to do that, because Excel doesn't have like an integrate function. So one way, well, I'm not going to do that. That's too long. We're just going to go back to that Wolfram Alpha page, and we're going to copy the number. 1.89217. It's not exact, but it's 6 sig figs. 1.89217. In fact, 4 subintervals got that to 6 significant figures. And so if I was going to sit here and calculate the relative errors, well then 4 subintervals already has 6 significant figures, so that's not going to do. But is there a way to make it tell me more? Okay. That's enough. I wish it would let me copy that. Plain text. There it is. Okay. Of course, you guys know it's not actually going to store that. It's going to only store this, because that's a double precision floating point. You guys see on the conference room board, what does a duck use to solve math problems? Is that Alex? Or who has that? I put that there. Alex there. Put the quackulator thing. How does a duck know exactly where it is floating on a lake? What?
It's like the missile because it knows where it is.
Huh? I was going to say because it has double precision floating point data. Okay, anyways. So now we got the true value. We can do error stuff. And for error stuff, I'm going to calculate the absolute error, or the actual error, and then the relative error. So absolute, let's get the absolute value of the approximation minus the true value. And then we can also calculate relative, which is the error divided by the true value. So Simpson's rule is really good. You can tell that even with 4 subintervals, it's like getting it super tiny, like 0.0004%. That's as good as you practically need it. But you can also tell that I'm supposed to be doubling this, right? I'm going from 1 to 2 and 2 to 4. I'm also doubling the number of subintervals we're using. Which means we should be reducing the error by a factor of 16. Let's see how close we are to reducing the absolute error by a factor of 16. If I take this absolute error and I reduce it, divide by 16, it's not exactly the same, right? But it's close. It's approximately 1/16 of the previous absolute error. And then if I take that error and divide by 16, I want you to notice it's not exactly the same number, but it's pretty close. So the absolute error is getting reduced by very, very close to a factor of 16 on each iteration of Simpson's method. So to summarize, I've shown you the same table I showed you last time we met, but the thing I've added is the column for Simpson's rule. It's a big step up over the midpoint Riemann sum, which is our previous best method, if you want to call it that. Because again, my error is shrinking faster, and it's got a better degree of exactness. Sorry, that's not the degree of exactness. That's the number of places I have to call the function in the subinterval. That's the degree of exactness. And then instead of shrinking by 1 over n squared, it's shrinking by 1 over n to the 4th when I use the composite rule. So what I would like you to be able to answer is this. What are some critical things to know about numerical analysis? What is the degree of exactness for every method we've studied so far? So on your test, I'm going to ask you, what's the degree of exactness for a left Riemann sum, a right Riemann sum, a midpoint Riemann sum, a trapezoid rule, a Simpson's rule? You should know it's 0.00113. How is the degree of exactness related to the asymptotic dependence on n? Whenever I said that question, what I mean is the absolute error is asymptotically proportional to what function of n when I use the composite rule. And you'll notice that when the degree of exactness is 0, it's 1 over n. When the degree of exactness is 1, it's 1 over n squared. When the degree of exactness is 3, it's 1 over n to the 4th. That's what I mean by that second bullet point. So even if we don't really care about integrating degree 3 polynomials exactly, I mean, who's sitting around integrating cubics all day long? It's really not that important. But what we really care about, the reason we want a higher degree of exactness is because it's going to make our error drop more quickly as we increase the number of subintervals in the composite rule. Last bullet point, how is the degree of exactness related to the lowest order derivative that appears in the error? What I mean by that is when the degree of exactness is 0, the first order derivative shows up in the first non-zero error term. When the degree of exactness is 1, then the second derivative shows up. When the degree of exactness is 3, then the fourth derivative shows up. And so those derivatives are kind of like the biggest actors on error. In other words, A Riemann sum is a pretty good approximation on places of your function that don't have a big slope. Like if your function just doesn't have a very big first derivative, then the Riemann sum is going to do a good job. The midpoint Riemann sum is okay with really steep slopes. The midpoint Riemann sum is only concerned if your second derivative has a large value. If the slope is changing quickly, that's when a midpoint Riemann sum is going to give you an issue. And then you could extend this argument and say, well, what about Simpson's rule? Simpson's rule is fine with a really steep slope. Simpson's rule is cool with having a big second and first derivative. Simpson's rule only starts to get screwy if your function has a really big fourth derivative. So if the derivative of the derivative of the derivative is changing quickly, then that's when Simpson's rule is going to start to give you an error. All right, we've got 20 minutes in class still. Dang. Okay, so let's talk about exercise 10. It says write a Python script that will implement Simpson's rule to approximate a given integral. The script should begin using just n equals 1 subinterval, then double the number of subintervals used on each iteration of a while loop until the estimated relative error is less than the threshold for 6 significant figures. Okay. So let me boot it up. We're going to do some coding today. Okay. So we're going to import numpy as np. And then we are going to give a place where we can define a function. Let's make it the natural log function. No, let's make it 1 divided by x. I'll tell you why here in a minute. We're going to give it a place to specify the lower bound and the upper bound. And then we are going to start off using 1 Simpson's rule subinterval. So I'll say n is equal to 1 for the number of subintervals. And then I'm going to create a while loop that says while my estimated relative error. When you saw that dialog box that says I need to update while the estimated relative error is greater than some tolerance, I'm going to do what? I'm going to try to calculate the Simpson's rule approximation, which is going to be well, let's do b minus a divided by 6 times f of a plus 4 times f of m plus f of b. So for the one thing I'm thinking about right now is like the a and the b for every subinterval is not going to be the same as the a and the b for the overall interval, right? And so maybe I'll name this a overall and b overall. So don't forget that those are the entire thing. And then I need to say something like for k equals 1 to n, no, for k in range n, I forget what language I'm doing, we get to do this, where a is going to be b overall, no, yeah, minus a overall, that's the width of my interval, divided by n. So that's the width of each subinterval times k. I should do it. And then b is equal to a plus the width of that interval. I don't even have to include the width of the interval inside the loop. That's just going to be there. So b minus a should just be the width. It should be w. W divided by 6. And m, I forgot m. So m is equal to a plus b divided by 2. And then I want my capital S to be something that grows over time. It's going to do a running sum of all of the Simpson's rules on the subintervals. So I do that, S equals S plus the new stuff. And then I need to define estimated relative error as being 1, just so it gets the loop started. My tolerance is going to be my number of significant figures. I don't know, it's going to be like 0.5 raised to the power negative number of significant figures or something like that. No, times 10 to the power negative significant figures. I can't remember if that's the exact formula. I need to look at that more closely. So how many significant figures do we want? 6. Then we need to calculate the error. So the error is going to be estimated relative error. I don't know what the true value is, and so I can't calculate the exact relative error, but I can estimate what the relative error might be by taking my previous approximation, which we call S old, minus my new approximation, we'll call S new, divided by S new. And for the new one, maybe we don't call it new, we just call it S. It doesn't have to be called new. And then we say, if the estimated relative error is still greater than the tolerance, we repeat the loop. And when we repeat the loop, we want n to be twice as many subintervals, right? So maybe that's good enough. We'll see if it works. Okay, so I forgot how to do exponents in Python. You got to do 2 asterisks when you want an exponent. Try that again. Division by 0. Of course, because 1 over x is going to be 0. But if my lower bound is 1 and my upper bound is 9, why would I ever be trying to divide by 0? That's not good. Oh, because that's supposed to be... My lower bound is supposed to be 8 overall plus the width times k. That's right. I should also print the answer and see if I get the answer right. So the answer is going to be S. All right, 2.548148. That sounds reasonable. I like it. All right, so that's what it looks like. Exercise 11 says, consider how we can calculate the value of the natural logarithm using integration, right? Because what's the antiderivative of 1 over x? Natural log of x. Yeah, thank you. So this is one way to define the natural logarithm. Let's use the Python script I developed in exercise 10 to calculate the value of natural log of 9. Oh, shoot. That's not right. That should be a 1. Is that a typo in your homework too? That 0 should be a 1. Yeah, I gotta make a note. Mental note. Fix typos in all my numerical analysis stuff. Yeah, no. So the natural logarithm should be the integral from 1 to x, because the natural log of 1 should be 0. So it makes sense that the lower bound of the integral should be 1. All right, now we want to use this Python script to evaluate the natural log of 9, and that means I want to take an integral from 1 to 9 of 1 over t dt. And I can use Simpson's rule approximation to approximate that. And so what did we just do? We took a Simpson's rule approximation of this integral from 1 to 9. So that should be the natural log of 9. Let's see if it works. Oh yeah. It's a little typo. I have to use NO for NumPy because I made a typo. Oh, I wonder if it's just log in NumPy. That must be log base 10, right? Because it's so far off. But then I wonder how do you get the natural log in NumPy? Oh, it says that is the logarithm. So that means my program is not working correctly, because it should not be that far off. It should be giving me the answer 2.19722. So what did I do wrong? Oh, you know what it is? This is an important lesson for everybody here. This estimated relative error, I think, is probably just a negative number because I forgot to put an absolute value around there. And so if that were a negative number, then it's going to count it as being less than the tolerance, even if it's a really big negative number. What I really need is the absolute value here so that it can only be less than the tolerance if it's a small number close to 0. Now let's try it. Okay, now let's also try. Whew, okay, so did we get 6 significant figures? 2.19722, 2.19722. Yeah. That's interesting. That is very interesting. So I'm going to have it print the answer every step along the way and how many subintervals it took to get that answer, and we'll see what happens. So with one subinterval, it gave me the answer 2.548. So Simpson's rule didn't really do that great with just one interval from 1 to 9. When we split it up into 2 subintervals, it got the answer 2.277, and then 2.21, 2.198, and you can see it getting better. But it took 128 subintervals from 1 to 9 in order to guarantee that these first 6 significant figures were accurate. If I only used 64 subintervals like this one, notice that it appears like the first 6 significant figures are correct, 2.19722, but if you looked at the next digit over and you rounded, then that 5 would actually round up to 2.19723, which would be wrong. So we really needed the full 128 subintervals to get to the right 6 significant figures there. That's way more than I was expecting, honestly, because I thought Simpson's rule was supposed to be like really good at doing this. It should be, right? Like the error should be decreasing by a factor of 16 every time. I'm going to try something else. I'm going to try exact relative error. No, heck, I'm going to do exact absolute error. And that's just going to be the absolute value of s minus what it's supposed to be, which is the logarithm of 9. And then let's print that instead of, or along with all of this, let's print the exact absolute error. And here's what I'm interested in. Is this exact absolute error decreasing by a factor of 16 every time? Like, is 0.35 divided by 16 equal to 0.08? I'm going to come up with a new variable, exact absolute error ratio. What this is going to do is it's going to take the exact absolute error and divide it by the new one. And that way I can see if this number is close to 16. This is what troubleshooting looks like. Okay. So ignore the first one. It's not going to be close to 16. Okay, but this only decreased by a factor of 4, then it decreased by a factor of 6, then it decreased by a factor of 9, then it decreased by a factor of 12, then it decreased by a factor of 14.5, then it decreased by a factor of 15.6, and then it decreased by a factor of 15.89. I actually really like this as an exercise. So you can see why we say it's asymptotically proportional to 1 over n to the fourth, is because the error wasn't always decreasing by a factor of 16. But in the limit, as we get these subintervals to be really thin, really tiny, we are getting closer and closer to seeing a reduction in absolute error by a factor of 16. Not at the start, but as you're getting close to the answer, it starts to reduce by a factor of 16 every time. So that's a great illustration of what it means to be asymptotically proportional. All right, thank you. Y'all have a good day.